Hey there, welcome back. This is Professor Hank, and in this video we will continue our discussion on binary search tree algorithms. Specifically, we're going to look at an algorithm for searching the binary tree, which we'll call find. Okay, the characteristics for this algorithm are going to be that it uses recursion, like all the other algorithms we've studied so far. It's going to return true if the key we're searching for is found, false otherwise. It's going to execute in linear time, big O of n, if the tree is degenerate, or it's going to execute in big O of log of n if the tree is nice and balanced, okay, a well-formed tree. And it's an algorithm where we're passing memory addresses by value. Okay, so here's what the algorithm looks like. As with previous algorithms that we've studied, our base case that's going to stop the recursion is going to be when r is equal to null, that is to say when the memory address that we pass to the algorithm is null, return false. Otherwise, we're going to check to see if the value in the node is a key that's equal to what we're searching for. Well, then we found what we're looking for. So we're going to go ahead and return true. Otherwise, if the value we're searching for is less than the key in the current node that we're examining, then we're going to look in the left subtree. Otherwise, we're going to look for the key in the right subtree. Okay, so here's our first example. We've got a very simple tree, one that contains 10, 20, and 30. Let's assume that we're going to search for 20. Okay, so what's going to happen is we initially call our find algorithm, and that's going to cause an instance of the algorithm to come into being and to start running. Okay, and I'll represent that instance by its parameter r, it's our parameter, and I'll refer to it as r sub 0. Multiple instances could be running at the same time, so I'll differentiate between the two with a subscript. So first thing that happens is r null? False. Then we're going to go ahead and check if the node that r is pointing at contains the value we're searching for. In this case, we're searching for 20. The node contains 20. Found what we're looking for, and algorithm's over. Find's going to return true. So x has got true. Okay. Now instead, let us assume that we were going to search for 30. If that was the case, then algorithm starts up. First instance checks the memory address that's passed to it's not null. Then it checks to see if the node it's examining contains the key we're looking for. We're looking for 30. This first node contains 20, so that's false. So then we have to determine, well, is the value that we're looking for, is it less than what's in the node we're currently examining? False. We recursively go to the right subtree to search for 30. Okay, so that's going to cause a second instance of the algorithm to start running, and we then check r for that instance. Does it contain null? No. Then we check to see if the node contains the key that we're looking for. In this case, it does. We're looking for 30, so that's true. Therefore, the algorithm says, let's go ahead and return true. Okay, so when we return true, that instance of the algorithm ends, and we return true back to the instance of the algorithm, in this case r sub 0, the value true. Okay, once that happens, then r sub 0, that instance of the algorithm, then returns and is finished, and it returns true. Okay, let's take a look at another example. So let's say that in this example we want to search for the value 41. Okay, well, we pass the root pointer to our algorithm, which gives our algorithm the memory address of the node that contains 40. Right, so we examine that. Is it null? No. Is that node containing the key we're looking for? No. Is 41 less than the key in the node that we're currently looking at? No. So that means that we're going to recursively take a look in the right subtree. Okay, so we go to that next node in the right subtree, and we repeat the process. Does that node, or is that memory address for that node null? No. Does that node contain the key we're looking for? No, it's 50 and we're looking for 41. Is the value we're looking for less than the key in that node? Yes, 41 is less than 50. So then we recursively examine or search for 41 in the left subtree of 50. So then we get to node 45. Is the memory address for that node null? No. Does that node contain the value we're looking for? No, we're looking for 41. Is 41 less than the key inside of that node? Yes. So we'll recursively search the left subtree. So we move down to node that contains 41. Okay, so is there a node there? Is the memory address for that node null? No. Does the node contain the key that we are looking for? Yes, it does. 41 matches 41, right? So notice that we had a total of, at that instance of time, 3 instances of the algorithm running. R0 started this search, right? And it's waiting for R1 to return, which in turn is waiting for R2 to return, which in turn is waiting for R3 to return, right? So once we've had our match of the value we're searching for with the key in the node that we're examining, then the last instance terminates and returns true back to the instance that called it. That instance terminates and returns true back to the instance that called it. That instance terminates and returns true back to the instance that called it. And then finally, the original instance of the algorithm returns true, leaving inside of X true. Okay? All right, now let us assume that we were searching for a value that is not in the tree. Okay? How would that play out? Well, let's assume for a second that we are searching for, value 68. Okay? Well, if we're searching for 68, then a similar kind of thing is going to happen, right? First instance of the algorithm is going to run past the root node. Is that memory address null? No. Does that node contain 68? No. Is 68 less than the key in that node? No. Therefore, we're going to move and search in the right subtree recursively. Okay, second instance of the algorithm begins. Is that memory location null? No. Is the value we're searching for in that node? No. Is the value that we are searching for less than the value in that node? No. So we're going to recursively continue our search in the right subtree. Okay. Another instance of the algorithm begins. Okay, so is the memory address that we've been passed null? No. Does that node contain 68? No, it contains 60. Is 68 less than what's in that node? No, 68 is greater than 60. So we're going to recursively search the right subtree. Okay. And we have another instance of this algorithm to run. Okay, so the memory address that's passed to instance R3, is that null? No. Is the value in the node whose memory address was passed to that instance, does it contain the key we're looking for? No, it contains 70, we're looking for 68. So then we ask the question, is 68 less than the value that's in the node we're examining? Yes. So then we would move to the left subtree. We recursively try to examine or continue the search in the left subtree. Well, there is no left subtree from node 70, right? Node 70 has no children. It's a leaf. So what we've passed to R4 is null. Okay, so that instance of the function hits its base case. So what does it do? Okay, it terminates and returns false back to the instance that called it, right? Now that the instance that called it has been returned to, it's done, and it in turn returns false back to the instance that called it. And then that instance completes and returns false back to the instance that called it. That instance terminates and then returns false back to the instance that called it. Finally, that instance terminates and returns false. Okay, so let's look at another example. In this example, we'll highlight the differences in performance between find algorithm executed in a well-formed tree, as shown on the left, and a find algorithm that's performed on a degenerate tree, as shown on the right. As indicated on the left side, this algorithm is going to execute with a running time of big O log of n. On the right side, it's going to be big O of n. The side on the left is going to be much faster than the example on the right. And let's see why. Okay, so let us assume that we are going to be searching for G, right? We're going to search for a key that's inside of the node G. Okay, so what's going to happen? First things first, we'll search in the first node, right? Node A. Didn't find what we're looking for. Okay, and since we didn't, that first failure to find what we're looking for is going to effectively cut our search space in half, right? If we don't find what we're looking for in that root node, because of the comparisons that we make within the find algorithm, we can eliminate this entire left subtree, which means we're never going to have to visit those nodes. Okay, so the next place that we're going to end up looking at is in node C. Right now, that's not what we're looking for either, and again, due to the questions that we ask in the algorithm, we end up cutting our remaining half in half yet again. Right, so that means that we're going to be able to ignore this subtree right here. Okay, two comparisons, we've eliminated roughly 3/4 of the tree that we have to actually examine. Now, next place we would look would be in G down here, right? We now have our match. So that's a total of 1, 2, 3 nodes we had to examine to find what we're looking for. Now, let's take a look at the degenerate tree on the right-hand side. You're going to see that the performance is going to be way worse. Okay, so initially we're going to start looking for the value that's located in G with the root node. Don't find what we're looking for. Then we're going to move on to the next node, B node, not going to find what we're looking for. Going to go to the C node, not find what we're looking for. Go to the D node, not find what we're looking for. Go to the E node, not find what we're looking for. Go to the F node, not find what we're looking for. And finally go to the G node, and then we find what we're looking for. So as you can see, we had to visit 1, 2, 3, 4, 5, 6, 7. All 7 nodes in the tree had to be visited before we found what we were looking for, right? Much, much, much slower than in the example on the left. Now, this is purely due, the difference in this performance is purely due to the size or the shape of the tree. In a well-formed, balanced tree, much faster, right? In this degenerate tree, where we have all of the nodes down this one line here that forms like a line, we have a much slower execution. Basically, in a degenerate tree, our find algorithm, its performance degrades to that of plain old linear search. Okay, so let's summarize. In this video, we examined an algorithm for searching for a key in a binary search tree. The algorithm that we use utilizes recursion, should utilize pass-by value so as to protect the pointers in the tree. The logic always returns something. The base case, if the memory address that we're examining for a node is null, returns false. If the node we're examining contains the key that we are looking for, then it's going to return true. Otherwise, if we're searching the left subtree, we're going to return the results of what we found. Otherwise, if we're searching the right subtree, we're going to return the results of what we found in the right subtree. And finally, the performance for this algorithm is going to depend on the shape of the tree. We saw that for a well-formed tree, we're going to have a running time that is big O of log of n. On the other hand, if the tree is degenerate, we saw that the running time for this algorithm degenerates into, which is big O of n. Okay, so that's going to bring this video to a close. If you felt that the video was useful, please consider giving the video a thumbs up. And if you thought that the video sucked, well, then you've got that thumbs down button as an option as well. If you'd like to see more videos, feel free to hit that subscribe button. And as usual, if you're a student of mine, feel free to drop me an email or to stop by my office hours. Okay, thanks for watching, and we'll see you next time.